So we've talked about resonance there, and I just want to move on and do this a little bit about the threshold of hearing. So the threshold of hearing at ordinary level, you just need a kind of a basic understanding of it. At higher level, there is a formula, and it's kind of an awkward one. So it's the smallest sound intensity detected by the average human ear at a frequency of 1,000 hertz. Okay, the number for it is 1 by 10 to the minus 12. It is a constant, so it's 1 by 10 to the minus 12. And then look at the units there, watts per meter squared. Okay, because the threshold of hearing relates to the sound intensity, that's where the unit comes from. Okay, so the sound intensity is power over area. I don't know if you remember much about power, but power is the energy per second. Okay, that's how we calculate power. We do energy over seconds, or work over seconds. So you can see here the sound intensity is at a point is the rate. So the rate is the per second part at which sound energy, so there's your energy, passes through a unit area. Okay, so they're the three parts. It's power over area. Power is actually energy and seconds, so that's why it's the rate at which sound energy passes through a unit area. So if you imagine I'm here and I've got a speaker or something, and that speaker is emitting a sound. Yeah. And then one of you is standing here and you've got a frame, and that frame is 1 meter squared, right? It's 1 meter by 1 meter. Okay, and to figure out the sound intensity at this point, we'd be analysing the amount of sound energy passing through that frame every second. And then if you have someone else, and that someone else is much further away from me, holding the same frame, 1 meter by 1 meter, the sound intensity at that point over here, the further away person, would be lower than it would be for the person that has the red arrow. Okay, there'd be more sound energy passing through the first frame per second than there would be passing through the second frame per second. Okay, and now just to briefly mention, and normally it's detailed in the question, but just to briefly mention that the area, because as I was saying to you before, so because when somebody emits a sound, or when a sound is emitted, it is emitted like a big bubble that expands and expands and expands. And the closer you are to that bubble, the more sound energy will pass by you per second. So you will have a higher sound intensity. And then as you get further away, because the bubble is growing and dispersing, there'll be less sound energy passing by you per second, so the sound intensity decreases. But because it expands like a bubble, the area we're normally talking about is the surface area of a sphere. So just when you're doing this formula, it's normally the surface area of a sphere that you're doing. Okay? There are calculations. I'm going to find one hopefully and give you one of them. The frequency response of the ear, just to briefly mention this. So over here, you have the sound intensity levels of things. So 0 here, which is equivalent to 1 by 10 to the minus 12. So these are, you can see at the top there, we don't tend to use the sound intensity scale because it's awkward. Like numbers like 1 by 10 to the minus 12, like scientific notation is awkward. Having to put that on a like a sign at an airport or something would be awkward. A lot of people don't understand that notation. They don't understand what a number like 1 by 10 to the minus 12 means. So they have a different scale, which is called the decibel scale. And the decibel scale is referred to as sound intensity level. Okay? So sound intensity level is measured in decibels. And then if I go down the bottom here, sound intensity is measured in watts per meter squared. Okay, and it's purely just for convenience that we don't use the decibel or the watts per meter squared, just because the numbers are really, really awkward. They're all in the region of 10 to the minus 12, and they would look silly, because you will actually notice in places like airports and stuff like that, like, you know, note high decibel reading or note over 130 decibels or whatever. So, you know, wear ear protection, that type of thing. So we have the decibel reading, the sound intensity level reading of, I suppose, normal sounds, you know, and it goes from very quiet up to uncommonly loud. Is that what it says? Uncomfortably loud, sorry. So yeah, we have a soft whisper, which would be 30 decibels, which would be considered very quiet. We have a business office, so I suppose that's just normal chatter, is about 55 decibels. A TV is 70, but I suppose that depends where you have it. A washing machine is 75, but again, I'd say that's very different decibel depending on where it is in its cycle. I know toward the end of my cycle of my washing machine's cycle, it's quite loud. So I don't know what the decibel reading was there. 85 decibels is kind of a cutoff point where it would be dangerous to be in 85 decibels for an entire day's work. So you'll see above this we have like trucks. You'd also have, you know, that jackhammer thing, you know, that breaks up concrete, and jet engine taken off. They would all have pretty high decibel readings. So you will notice that, like at airports, people who work as baggage handlers or, you know, have jobs like that where they're out near the airplanes, they wear ear protection. People who work at train stations, things like that, they would have ear protection. People who work in construction would wear ear protection. It's all because those decibel readings are quite high, so to be around them for any extended period of time is damaging and dangerous to your ears. Okay, now the frequency response of the ear. So the ear, like other things, has a natural frequency. So if it has a natural frequency, then that means it can be matched. And if it can be matched, that means you get resonance. Okay, and the natural frequency, it says here, so the ear is most sensitive between 2000 and 4000 hertz, and it will kind of vary from person to person depending on the makeup of your ear, the length of your ear canal, the size of your eardrum, things like that. Like obviously natural things that will change the natural frequency of your ear. So the natural frequency of the ear is between 2000 and 4000 hertz. So let's say the natural frequency of my ear is 3000 hertz. And then if I hear a sound that has a natural frequency, that has a frequency of 3000 hertz, I will have matching frequencies. If I have matching frequencies, that means I have resonance. And if I have resonance, then I get a transfer of energy, which causes an increase in amplitude. And to my ear, an increase in amplitude will make the sound appear to be louder. So our ear is more sensitive to sounds that are very, very close to the natural frequency of our ear. Okay, so if you get like a sound level meter or something like that, the sound level meter is designed to act like your ear. So it will be set up to be more sensitive within these frequencies. So if a sound has a frequency between 2000 and 4000 hertz, the sound level meter, just like your ear, will recognize the fact that resonance would occur. You'd get an increase in amplitude, and an increase in amplitude means, because we know that bigger amplitudes means louder sounds, so it would appear louder to our ear. Is that all right? Sound intensity level I already talked about. So sound intensity level is the decibel scale, and it's just a more suitable scale because we're using numbers that people understand. So if you say to someone, the sound here is over 100 decibels, please wear ear protection. Like if you said to someone, the sound here is 9.6 by 10 to the minus 12 watts per meter squared, please wear ear protection. Those numbers just don't mean as much. Okay, so that's why there is another scale. Now you do need to know how to, where is it? Oh yeah, here it is. So you need to know how to convert between them. And this is how. When the sound intensity, so the number in watts per meter squared, doubles, the sound intensity level increases by 3. Okay, so if the sound intensity level doubles, you add 3 to the sound intensity level. Did I say that right? If the sound intensity in watts per meter squared doubles, you add 3 to the decibel number, the sound intensity level. Okay, so if the sound intensity were to multiply by a factor of 4, that would mean it has doubled twice, so we would add 6 to the sound intensity level. Okay, that's really important. You need to be able to make that conversion between them. Okay, and the last thing here is, I've kind of talked about this already, so the sound level meter, a sound level meter uses what's called decibel adapted scale. Decibel adapted scale is that it reacts like the human ear, so it is more sensitive between 2000 and 4000 hertz. And so yeah, because of the natural frequency of the ear being in that scale, I'm actually going to write this down. So natural frequency of ear is between 2000 hertz and 4000 hertz. Yeah? So then if you hear a sound with a frequency in this range, resonance will occur. Resonance will cause a transfer of energy. That transfer happens because the frequencies match. And then that causes an increase in amplitude of the wave. And then if you have an increase in amplitude of the wave, what we'll hear because of the increase in amplitude is a louder sound. And the sound level meter works like that. It's adapted to work the same as the human ear. So that's what the decibel adapted scale means. Okay, and then this last bit here is about noise pollution and ear protection. So I was talking about that with the airport. So if you work in a job where you're exposed to high decibel levels for an extended period of time, that you have to wear ear protection. So they have it over here. So 90 decibels, max of 8 hours per day. 93 decibels, it goes down to 4. So you're getting, as the decibel reading goes up, you get quite a large kind of decrease in the amount of hours that you can expose yourself to that sound without wearing ear protection. Okay, so take down all of your notes on that. I haven't added in the questions yet, but I'm going to add in a question here and a question here. They're going to be for next week though, so I'm not going to give you another question tomorrow. All right, so take down your notes and then attempt the questions, but please make sure that you have the questions ready for me tomorrow that I gave you last week. I'm going to take them up.